Okay, so we're working on homework 2.4, motion with constant acceleration. And specifically, it's question number 5 that we're going to be focusing on here. Or really 5 part B, because part A, you need to kind of predict what you think the relationship between stopping distance and initial velocity is. But 5B is where we're going to actually calculate it. So let's write down what we're told in question 5, and then we'll move on to compare some stopping distances. So we're told that our brakes of our car create a constant deceleration of 4.2 meters per second squared. What that means is, deceleration means that our acceleration is going to be negative 4.2 meters per second. That is, the brakes act in the opposite direction that our car is moving. So it serves to slow them down, which is good because that's what brakes are supposed to do. And it's regardless of how fast you're driving. So we're going to be comparing two speeds and comparing the stopping distance of those two speeds. So our VI, or I'm going to call it VI1, is 16 meters per second. And we're also told, well, that the other speed, VI2, is going to be 32 meters per second. So these are both the initial velocities of, we'll say, two different cars, or maybe the same car, but tested at two different speeds. But either way, the final velocity of the VF is intended to be 0 meters per second. If both of these cars are to decelerate to stop, that's going to be our final velocity. So the question is, what is a stopping distance? Stopping distance 1, and what's our stopping distance, or our change in displacement, 2? Well, let's calculate these both independently of each other, and then we'll simply compare our two answers. Because really the question in part A was, how does the speed determine your stopping distance? Well, we have acceleration, we have initial velocity, or really two initial velocities, and we have a final velocity. We need to find our displacement, or how long it takes to slow from each speed to 0. Well, equation 5 of our derived acceleration velocity equations should do that for us. Equation 5, let's see, I'll write it up above here. If you recall, was final velocity squared equals initial velocity squared plus 2 times a, or acceleration, times the displacement, or delta x. Well, to solve for delta x, we can move the vi squared to the other side, so it's vf squared minus vi squared equals 2 times a times the displacement. And then if we divide both sides by 2a, that means our displacement, or the stopping distance, is going to be vf squared minus vi squared all over 2a. So let's make this side 1 right here, or speed 1. This is going to be speed or velocity 2. Excuse me, and we're going to be solving for delta x. So our change in displacement 1 is going to be vf. Well, I should actually put the value in for it. We know that already. We know it's going to be vf. What's vf? Well, in both circumstances, it's 0 meters per second, the quantity squared, minus vi, or vi1, because we're testing the first velocity, 16 meters per second, the quantity squared, all over 2 times the acceleration. The acceleration is negative 4.2 meters per second squared. And you know what? I just realized up here I forgot to put the squared in there, in the acceleration up top. So that was my fault. That should be meters per second squared. So our acceleration is negative 4.2 meters per second squared. If we calculate that out, that means that our displacement, or displacement 1, is going to be 30.5 meters. So all these other units cancel out, and we have an answer in meters. Well, now let's do the exact same thing, but we're going to simply substitute v initial 1 with v initial 2. So let's do in scenario 2 here. Remember our delta x change in displacement is vf squared minus vi squared all over 2a. So our change in displacement 2 is going to be 0 meters per second squared, the quantity, I'm sorry, squared, minus vi2, that's 32 meters per second, the quantity squared, all over 2 times the acceleration. That is, acceleration is 2 times negative 4.2 meters per second squared. If we punch this into our calculator and solve for the change in displacement, we're going to find that our change in displacement 2 is going to be 122 meters. So we have a difference of velocity of 2 times, but in terms of stopping distance, we have a difference stopping distance of 4 times. That's 4 times right there. So if you double your speed, it's going to take you 4 times as far or 4 times as much distance to be able to stop.